This example concerns Newton's law of cooling, which states that the rate of change in temperature of an object will be proportional to the difference between the object's temperature and the temperature of the surroundings. Let y represent the temperature of an object in a room where the constant temperature of the room is 45 degrees. The object starts out very hot at 240 degrees, but it cools to 120 degrees after 20 minutes. If we use Newton's law of cooling, how much longer should it take for the temperature of this object to decrease to 80 degrees? So let's just draw the situation. There's a room where the ambient temperature, I'll call it T room, is 45 degrees. There's an object in the room. The temperature of the object in the room is 240 degrees at T equals 0. So it's hot. And the surroundings are cooler. Over time, what's going to happen to the temperature is that it'll approach 45 degrees as an asymptote. Starting off at 240, okay, so let's write the differential equation. That the rate of change of the object's temperature is going to equal a constant times the difference in that object's temperature and 45 degrees. This is the differential equation. What we want to do next is try to solve it by separation of variables for the general solution. And I'm going to rewrite y prime as dy over dt. Put y minus 45 in the denominator on the left, and then multiply the dt to the other side. We would now want to take an antiderivative of both sides. This is going to leave us with ln y minus 45 on the left and kt plus c on the right. I'll let both sides of the equation become an exponent of an e. That'll cause these to cancel, and we get this. Finally, add 45 to the other side, and we arrive at the general solution to the differential equation. Next, we want to figure out, using the data that they gave, what is the correct value of C for our particular curve. They said after 20 minutes, the object gets to a temperature of 120 degrees. We're going to let T equal 20 and let the temperature be 120. So let's plug those in. The general solution was y equals CE to the KT plus 45. So let's let y be 120, let t be 20, and we have to determine both c and k. So we can't do it just with that data point alone. We also have to use our initial data point that we're going to start at 0, 240. So let's create a system of equations. We're going to let t be 0 and let y be 240. C is 195. Plug that in over here. And we could finally solve for K. I'll take an ln of both sides. There's my K. Now we can construct the function. And we can use it to make a prediction. How long does it take for the temperature to reach 80 degrees? So let y equal 80 degrees. I get 35.95 minutes. Keep in mind that that is a time elapsed from the beginning of the clock. The clock started when the object was 240 degrees. And so the question asks, how much longer does it take for the temperature to decrease from 120 to 80? So they're really just talking about this interval here. So we have to do a little subtraction to get the actual difference in time. It's going to be 35.95 minus 20, 15.95.